Hello my dear students, welcome to my channel Dey Sir's Chemistry Coaching. Let's start the second part of expected questions and answers of chemical kinetics. This is the very important question. See the question, how the rate of a reaction depends on temperature. You see, the rate is directly proportional to temperature. If temperature increases, the rate of reaction also increases. It has been seen that for every 10-degree rise in temperature, the rate becomes double. It is due to 10-degree rise in temperature, the number of effective collision of the reactants becomes double. Do you know what are effective collisions? Effective collisions are those by which the reactants directly change into product. You know that during any reaction there is one energy barrier, minimum energy barrier called threshold energy. The reactants after collision should change into product. If temperature is applied to the reactants, the number of collision of the reactant increases and most of the reactants can easily overcome the minimum energy barrier, that is threshold energy, and change into product. So those collisions of the reactants which directly change into product called effective collision. Clear, I think? Once again, see it. When temperature increases, most of the reactants directly change into product because the rate of a reaction is directly proportional to the temperature. Experimentally, it has been proved that for every 10-degree rise in temperature, the reaction rate becomes double because the number of effective collision also becomes double. Now the second question is how the rate of a reaction change with catalyst. How the rate of a reaction depends on catalyst. You know that catalysts are the substances which take part in the reaction, but at the end there is no change of them. So second question, catalyst. How the rate of the reaction depends on catalyst. Remember it. A catalyst generally increases the rate of a reaction. There are some catalysts also which decreases, but in most of the reactions catalysts are used to increase the rate of a reaction. Why? Because the catalyst decreases the activation energy of the reaction. For example, understand it. First, see the answer. A catalyst increases the rate of a reaction as a catalyst decreases, this is very important point, okay, decreases the activation energy of a reaction by applying a suitable path for the reaction. So listen, understand it. So you see that a catalyst generally increases the rate of a reaction as a catalyst decreases the activation energy of a reaction by applying a suitable path for the reaction. Just understand it. There are some reactions which at normal conditions either does not occur or becomes very slow. If we want to speed up the rate of a reaction, sometimes we use catalyst. Say for a reaction 50 kilojoule of energy is required so that the reactants will change into product. That extra 50 kilojoule is called activation energy. If we use a catalyst, what happens then? A catalyst reduces the activation energy. Say, if we use a catalyst, only 20 kilojoule is required from outside so that the reactants easily change into product. That's why it is said that a catalyst decreases the activation energy of a reaction. How it becomes? A catalyst chooses a suitable path so that the reactants can easily change into product. That is similar to shortcut process. Okay, you see, in hill area, if you want to go from one side to other, you need walking a much more. But if you follow the steps, within a certain minute you will reach. A catalyst follows the steps, that is shortcut way, so that the reactant easily change into product. Now the next question is, how the rate of a reaction depends. How the rate of a reaction depends on the surface area of the reactants. On the surface area of the reactants. Listen, if you consider example, this is a piece of wood. This is a piece of wood. If the same wood is pulverized, that is, make it dust, wood, powdered form, just burn it. You see, powdered form of wood burns faster because the surface area. So greater the surface area, greater will be the rate of a reaction. So you see that greater the surface area, more faster will be the rate of a reaction. That's why you can conclude that the rate of a reaction directly proportional to the surface area of the reactant. Greater the surface area, greater. For example, powdered wood burns faster than a lump of wood. For example, powdered wood burns faster than a piece of wood. I think you understand that. The fourth topic, how the rate of a reaction depends on the concentration of the reactants. How the rate depends on the concentration of the reactants. Very easy. If the concentration of reactant becomes more, the rate becomes more, because more number of reactant particles directly change into product. So what is the answer? If the concentration of the reactants increases, the rate also increases. Now the next part, listen now. For first order and for zero order reaction, there is one integrated rate equation, and you will get question from that integrated rate equation. Actually numericals you will get. So try to understand the formula and numericals of integrated rate equation as well as half-life period for first order and zero order reaction. So the next topic is, listen, it is integrated rate law equation for first order and for zero order. You know, in your syllabus there is only first and zero order reactions are there, okay? So see, the integrated rate equation for first order reaction is K equals to 2.303 by T log A naught by AT, and for zero order reaction KT equals to A naught minus AT. What is A naught? A naught is initial concentration of the reactant, the amount of reactant taken in the beginning of the reaction, that is called initial concentration. And AT is the concentration of reactant remain at time t. For example, say 80% of the reaction is completed. So remember it, whenever percentage is given, always consider the initial concentration as 100. If 80% is completed, 80% of the reaction is consumed, 80% amount of the reactant is finished. So what is remaining? 100 minus 80, that is 20. Okay. So listen, in this type of reaction, two parts are there. In the first part, first order reaction is 80% completed in 20 minutes. In this chapter, if the time is in second, keep it second. If the time is in minute, keep it in minute. If the time is given in hour, don't change it. So this is the first part. From the first part, find the value of K, that is rate constant. As the rate constant is not asked here, so K equals to this much, only put it. In the second part, time is asked to determine. So put the value of K and determine it, okay? Now let's start. See the again reaction of first part. A first order reaction is 80% completed in 20 minutes. How to write the answer? So the answer is, this is given. First order reaction is this. I have already told you that if percentage is given, always consider the initial concentration as 100. So initial concentration of reactant is 100, and how much it is remaining? Obviously 80% is completed, so we get 800 minus 80, that is 20, and the time is given already, that is 20 minutes. Don't change in second, keep it in minute. Put into the formula, find the value of K, because it is a two-stage numericals. T is 20 log A naught, that is 100, and AT is 20. How to calculate it? 2.303 by 20 log. Now you know that log A minus log B. Log A by B equals to, this is the formula, log A by B equals to log A minus log B. So put into the same, log 100 minus log 20. You may ask me why you have not cancelled it. If you cancel it, it becomes 5, but the value of log 5 is not given in the question. Listen, the value of log 5 is not given the question. Log table is not supplied. That's why. And you know that log 100 equals to 2, log 10 equals to 1, and log 1000 30, so it is 3. Log 10 10 1, log 100 20 2, log 1000 30 3. That's why just put it 2.303 by 20, log 100 means 2 minus log 20 given 0.3010. Now don't calculate too much, just subtract it and write it. Now put the same value into the second part. What is the second part? See the second part. The second part is T to be calculated, 90% is completed. This is the second part, T to be calculated and 90% is completed. So the T equals to 2.303 by K log 100. The initial concentration remains the same, okay, because the same reaction is going on. So it is 100 minus 90. Now put the value of K, here it is the value of K, you have find out, put the value of K, 2.303 by K is 2.303, 20 comes up into 20 into this 2 minus 0.3010. And how to calculate log? Log 100 by 10, that is log 10. And you know that log 10 1, so the answer becomes, cancel it. So 20 into, just subtract 2 minus 0.3010 and you get the answer. As time is asked, so obviously this is in minute. That's the answer. So I think you understand it. This is very important questions. If you do only this question, you can get any one. So let's do one numericals from zero order reaction, okay. Let's do one numerical for zero order reaction. Clear? Let's do one numerical for zero order reaction. So write the question. For the reaction ammonia heated in presence of platinum catalyst to get nitrogen and hydrogen, follows zero order, okay. The value of rate constant is the value of K equals to, say it is 2.4 into 10 to the power minus 2. The value of K equals to 2.4 10 to the power minus 2 mole per liter per second. It is given. How much time will it take to change the concentration of reactant from 0.30 mole to 0.10 mole. So follow the reaction, remember it. This is also an example of zero order reaction. When ammonia is heated in presence of platinum, it changes to nitrogen and hydrogen. Remember it, this is an example of zero order reaction. Another, I have already told you that a zero order reaction is any photochemical reaction, that also I have told you. K given. Calculate the time taken to reduce the initial concentration of reactant, that is 0.30 to the remaining. Put in this formula, put directly this formula, okay. Put into the formula, the value of K is given, you have to calculate the time. So T equals to, so put into the formula. You know that for zero order reaction, the integrated rate equation is, for zero order reaction, the integrated rate equation is this. So time taken equals to 1 upon K into A naught minus AT. Now K is given 1 upon 2.4 into 10 to the power minus 2, and AT how much is given? A naught initial concentration 0.30 minus, it will directly change, don't subtract, directly change it, 0.10 molar, okay. So calculate it and get the answer. Comes up 100, for point, for decimal another 0, 24, and here 0.20. So just calculate it, okay, equals to 100 into 10 into 20, 24, for 800, cancel 100, so it is 200 by 24. So it is just 8 point something, okay, 8.3. So the time is asked to determine, and here I have already given second inverse, so it is in second, that's the answer. So you understand it, okay, I think you understand it. Now the next topics, that is half-life period. You know that what is half-life period? It is the time taken to reduce the initial concentration of the reactant to just half of it. So half-life period is the time taken to reduce the initial concentration of the reactant to half of it. For first order reaction, the half-life period is independent on the initial concentration of reactant. But for zero order reaction, the half-life period is directly proportional to the initial concentration of reactant. So just understand the half-life period. So listen, the half-life time, that is the half-life period or time, it is the time taken to reduce the initial concentration of the reactant to half of it. For example, say the initial concentration of a reactant is 100 moles per liter. Say the reaction takes 10 minutes to complete, but after 6 minutes it has been found that 50% of the initial concentration of reactant is reduced. That is, after 6 minutes 100 moles per liter, that is the initial concentration of reactant, reduces to 50 mole per liter. So this 6 minutes is called half-life time or half-life period. In other ways, you can say half-life period is the time taken to complete half of the reaction, but it is better to say it. For first order reaction, the half-life time or period is 0.693 by K. So you can say that for first order reaction, half-life time is independent on the initial concentration of the reactant. For zero order reaction, the half-life time is equal to A naught, that is initial concentration, by 2K. K is the constant. So you can conclude that the half-life period of first order reaction is independent on the initial concentration of reactant, and for zero order reaction the half-life period is directly proportional to initial. This is very important. Okay, this is very important for term 2. The half-life period for first order reaction is independent on the initial concentration of reactants, while the half-life period for zero order reaction, half-life period is directly proportional to the initial concentration of reactant. This point is very important for your term 2 exam. Okay, now the numericals relating to half-life period, direct numericals will come, and see the numericals. Okay, see the numericals. Question: proof that, this is very important for your term 2, proof that the time taken to complete 99.9% of a reaction is 10 times of half-life period, that is T half, for a first order reaction. So this is very important. Okay, see the answer. The time taken to complete 99.9% of a first order reaction, that is to prove time taken to complete 99.9% of the reaction is 10 times of half-life. Therefore, time taken to complete 99.9% divided by half-life, you know the formula of half-life, 10 to prove it. Just find it. Half-life, you know the formula, divide it, you get 10. See the answer. Time taken to complete 99.9% equals to, apply the formula, 2.303 by K, put K as it is, log. I have already told you, when percentage is given, then consider the initial concentration of reactant as 100. 99.9% of the reaction is completed, so the remaining 100 minus 99.9 equals to 2.303 by K log 100 minus 0.1 equals to 2.303 by K log 1000. Just 0.0 comes up. And you know that log 10 equals to 1, log 100 equals to 2, log 1000 equals to 3. So equals to 2.303 by K into 3, that is T 99.9%. We get it. T half also we know it. Okay, what is the formula of T half? You know the T half. Now T half equals to half-life period 0.693 by K, because the reaction is of first order, that is mentioned. Just divided the two. So now just divided it, you get the answer. Okay, very important it is. So T 99.9% by T half equals to 2.303 by K into 3 divided by T half, 0.693 into K. So it is nearly equivalent to 9.9, that is 10. So it is proved. This is very important. Okay, this is very important question for your time. So the last question, I think you get it, the point. So remember it. The next question, okay. Do you know what is elementary reaction? What is elementary reaction? So question is, what is elementary reaction? What is elementary reaction? ELIMENTARY, elementary reaction. Remember it, if a reaction occurs in single step, that is called elementary reaction. And if a reaction occurs in multiple step, that is called complex reaction. For a complex reaction, one step is the slowest step, and that slowest step is called rate determining step. So remember it, if any reaction occurs in single step, it is called elementary reaction. There are number of examples, but you can write the example of hydrogen when reacts with iodine changes to hydrogen iodide. This is a very good example of elementary reaction. Okay, and if any reaction occurs in multiple step, that is called complex reaction. Extra, if a reaction occurs in 2 or more steps, they are called complex reactions. And remember it, during a complex reaction, one step is the slowest step. That slowest step is called rate determining step. So remember it, in a complex reaction, the slowest step is called rate determining step. So write down continuation, in a complex reaction, the slowest step is called rate determining step. So I think you understand it. Another question that is very important for your term 2 exam. Okay, the question is, define average life and instantaneous life of a reaction. So see the reaction question is, define average life and average rate, better to write average rate and instantaneous rate of a reaction. Now listen, understand it, okay? Directly you will get it in your NCERT. So just understand. Say a reaction takes place 5 minutes to complete. So the average rate is, say 100 moles of the reactant becomes 0 moles. Say 100 moles of reactant finished and 100 moles of product you get. So the change of concentration of reactant or product by change in time is the average rate. But if you say after 2 minutes, what will be the rate? After 3 minutes, 4, 5, 6, 7, 8 minutes. So this is called instantaneous rate. Once again, say if the reaction takes place 10 minutes to complete, say after 2, 3, 4 or any instant of time, the change of concentration of reactant or product is called instantaneous rate. So this is important questions. So the total change of the concentration of reactant or product per unit time is called average rate. The change of concentration of reactant or product at any instant of time is called instantaneous rate. I think you understand it. Okay, so please watch my next video. Or